And this is the Oseberg ship. There's another one on this side, which is the Gokstad ship. And tucked around the corner is the tuna ship. But just at the back here, there are all these wonderful artifacts that were found. The Oseberg ship was a burial ship. So on the ship was found the remains of 2 ladies and all these wonderful artifacts. Wagons, caskets, sledges, beds. But you can't get anywhere near them now. They're so fragile, they've decayed away. All that's holding them together is the outside lacquer. These are under serious threat. The ships themselves are also under threat, but not under immediate threat. And that's because of the decay. Once you get the things out of blue clay, where they're preserved, they start to decay. So the Oseberg ship, for example, was excavated in 1904. And the first thing they had to do was to stop the wood from shrinking when it dried, because it would destroy all the intricate patterns that were found and all on the artifacts, all the wonderful carvings and things. So what they used was a material called alum. Now at school, maybe you remember growing these copper sulfate and alum crystals. Remember you used to grow a little crystal in this. So alum is a simple salt of potassium and aluminium sulfate that forms these crystals. And by injecting hot alum into these objects, when the alum cools, it forms crystals, and this gives the wood its strength. So when the wood dries after being excavated, it doesn't shrink, it retains its shape. And that's worked brilliantly over the last, well, up to the last 100 years, not recently. But what the conservators didn't realise was that over the years, alum reacted with the humidity in the Viking ship hulls, catalysed by the iron nails and rivets, to give sulfuric acid. Now, sulfuric acid isn't good, okay? Because sulfuric acid over the years has decayed away all the wood fibre, all the cellulose, all the lignin, well, almost all of it has gone. So Norway's national treasure is under immediate threat. So these objects are at serious risk of crumbling away. Look okay on the outside, but on the inside, they're rotten. So last year was the first meeting of the Saving Oseberg Research Group. And I'm proud to say I'm a member of this group. And although I work at Nottingham, the University of Oslo is planning on giving me what's called an adjunct professorship. That means 20% of my time is spent over in Oslo or working on this project. And the Saving Oseberg laboratories have gone up just behind the ship museum. The Norwegian government's just given a grant of 50 million kroners, that's £5 million, to try and get this right. Look at it, it's absolutely rotten. The white bits are what's left of the alum crystals. If you look at this using a technique known as scanning electron microscopy, where we use high energy electrons which behave as waves, like light waves, so you can produce an image. And you can see this highly magnified wood fibre. You can see all these holes within the wood. All the cellulose and virtually all the lignin has gone. These large pieces here are the alum crystals. So we've got to replace the cellulose and lignin with what's called a consolidant. And it has to be a natural polymer. We can't just use plastic. They don't want a plastic boat or plastic artifacts. That won't do. So it's got to be something which is carbohydrate, wood-like, which to replace the lost cellulose and lignin. This is our task. This is the task of the research group. And amazingly, Norway may have its own natural resource to solve the problem. The Norwegian coastline, lots of fields, yes, and lots of these rascals, the crabs, okay? And the crabs on the shells have this remarkable polymer called chitin, which gives the crab its rigid, firm structure, appearance, stops it from falling apart, and also keeps it dry it stops the inside of the crab from evaporating. It stops also seawater from getting in. Now the chitin, this material, can be modified to give this marvellous polymer called chitosan. So chitosan, this is like the cellulose, but it's got these special groups on it which can be used to reduce the acid in the wood and also take out the metal ions which are causing all the problem. Jenny is one of 3 PhD students working on the project. Jenny's with me in Nottingham, but there's Emily in Norway, another student working in Italy on the problem. And this is a picture of the chitosan molecule magnified 1 million times. I'm sounding like Brian Cox now, aren't I? 1 million times. And it's a rigid type of polymer which, if we can get it inside the wood, will give the wood its strength back. And it's very like the original cellulose in its properties. And we can further modify the chitosan by various chemical reactions to make it longer lasting. The problem then is to try and get it into the wood to give the wood its strength back. That's our task over the next 2 or 3 years to get this sorted. If we fail, the consequences are disastrous. Okay, so we have to get right. And fortunately, there's lots of test wood that was discovered with the ships, which we can try these theories out. So let's hope that these things will remain. And then when we visit the ship museum again, it's not just all blank spaces at the back of the museum. That wouldn't do, would it? No. So that's sort of chemistry in action.